Now let us talk about the exercise 1.1 of NCERT book. So this is the first question, and x is equal to 5, then y is equal to 3 5s are 15, but 15 is not contained in set A. So this does not belong to A. So 5 comma 15 will not be an element of R. So now if we take x is equal to 6, 7, 8 and so on to 14, the value of y will not be contained by A, so that's it. Possible ordered pairs of relation are these four ordered pairs. So if we write the relation in roster form, we write. Now we have to check the reflexivity. So as we know, domain is A, and A is the set of all the numbers from 1 to 14. So it is not reflexive because no element of domain is related to itself. That is, there is no 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and so on to 14, 14. No element is related to itself. So we write 1, 1, 2, 2 and so on to 14, 14 do not belong to R. So R is not reflexive. Now let us talk about symmetry. As we have discussed, the symmetry is the characteristic of a relation where every element has its reverse. That means if there is 1, 3, there must be 1, 3, 1. If there is 2, 6, there should be 6, 2. And if there is 3, 9, there should be 9, 3 and so on. So as we have observed in the relation, 1, 3 is there, but 3, 1 is not there. 2, 6 is there, but 6, 2 is not there. 3, 9 is there, but 9, 3 is not there. 4, 12 is there, but 4 is not there. So we write 1, 3 belongs to R, but 3, 1 does not belong to R. We may give this reason for every ordered pair, though write only 1, 3 belongs to R, but 3, 1 does not belong to R. It is sufficient to give this is not symmetrical. So we may say that R is not symmetric. So it is neither reflexive nor symmetric. Now we have to check transitivity. First we have to observe whether transitivity may be checked or not. So there must be two ordered pairs such that the second component of one ordered pair must be identical to first element of the second ordered pair, that is here. So transitivity of the relation may be checked. So if 1 is related to 3 and 3 is related to 9, so for transitivity there must be 1, 9 in the relation, but it is not. Again I repeat, 1, 3 is there, 3, 9 is there, so 1, 9 should be there, but it is not here. So we may write it as 1, 3 belongs to R and 3, 9 belongs to R, but 1, 9 does not belong to R. So R is not transitive. Thus we may conclude that R is neither reflexive nor symmetric nor transitive. Now second part of first question is R is a relation in a set capital N, where capital N indicates the set of all the natural numbers. R is a relation in a set means domain and codomain both are the same set N, and R is defined as a set of ordered pair x, y, where y is given as x plus 5, where x is less than 4. So x belongs to domain, that is natural numbers, and x is less than 4. That means x can have any natural number value which is less than 4. So we may write it as 1, 2, 3. These three possible values. Relation is y is equal to x plus 5. So for x is equal to 1, if we substitute here, we get 5 plus 1, 6. And if we substitute 2 here, 2 plus 5, 7. And if we substitute x is equal to 3 here, we get 3 plus 5, 8. So y can have 6, 7, 8. For 1, y can have 6. For 2, x is equal to 2, y can have the value 7. For x is equal to 3, y is equal to 8. So the roster form of the relation is the set of ordered pairs 1, 6, 2, 7, and 3, 8. Now let us talk about reflexivity, symmetry, and transitivity of relation. So reflexivity. Since each and every element of domain, that is set of all natural numbers, every element is not related to itself, that is there is no 1, 1, 2, 2, 3, 3, 4, 4 and so on. So we may write arbitrarily for all a belongs to n, a comma a does not belong to r, so r is not reflexive. Now let us talk about symmetry. So as we observe, 1, 6 is there but not 6, 1, 2, is there but there is no 7, 2, and 3, 8 is there but not 8, 3. So reverse of any ordered pair is not contained by relation. So we may write 1, 6 belongs to R but 6, 1 does not belong to R, and the same reason for may be given for these two ordered pairs. So we may say that R is not symmetric. Now let us talk about transitivity. For transitivity, we need two ordered pairs, as I have told you, such that the second component of one ordered pair must be equal to first component of some other ordered pair, which is not available here in this relation. So that means transitivity of this relation may not be checked. As I said, if transitivity of a relation may not be checked, it is considered to be a transitive relation, because we may say that transitivity criterion is not violated because it cannot be checked here. So R is transitive. Since transitivity of R cannot be checked. Now we come to third part of first sum. This is a relation in a set A where A is defined as a set of 1, 2, 3, 4, 5, 6 and R is defined as a set of ordered pairs x, y where y is divisible by x. That is, the second component of every ordered pair must be divisible by first component of the ordered pair. So as we know that one can divide each and every number, so if we write the roster form of the relation with 1 as first component, every element of A can be contained, because 1 can divide 1, 1 can divide 2, 1 can divide 3, similarly 1, 4, 1, 5, 1, 6. Now if we take first component 2, so 2 can divide 2 and 2 can divide 4, 2 can divide 6. Now if we take 3, so 3 can divide 3, 3 can divide 6. If we take first element as 4, so 4 can divide only 4 out of these 6 numbers. So only 4, 4 is there. If we take 5 as first component, so only 5, 5 can be written, because 5 can divide 5 only out of these 6 numbers. Similarly, 6 can divide 6, so only. So this is the roster form of relation. Now we have to check the reflexivity, symmetry and transitivity. So first, reflexivity. As you see, 1 comma 1 is there, 2 comma 2 is there, 3 comma 3, 4 comma 4, 5 comma 5, 6 comma 6. That means each and every element of set A is related to itself. So general statement for A belongs to capital A comma A belongs to R. So R is reflexive. Now let us talk about symmetry. For symmetry, the reverse of every ordered pair must be contained by the relation. So if we observe, 1 comma 2 is there, but 2 comma 1 is not there. 1 comma 3 is there, but 3 comma 1 is not there. So there are so many ordered pairs, 2 comma 4, 2 comma 6, 3 comma 6, whose reverse are not contained by the relation. So in general, we may say that for all A comma B belongs to A comma B belongs to R, implies that B comma A does not belong to R. So R is not symmetric. Now let us talk about transitivity. So first we have to observe whether the transitivity of the relation may be checked or not. So first we see 1 comma 2 is there. Second component, this ordered pair is identical to first component of this ordered pair. So first component of this ordered pair is related to second component of this ordered pair, that is 1 comma 2, which is this ordered pair itself. If we check 1 comma 2 and 2 comma 6, so 1 comma 6 is also there. 1 comma 2, 2 comma 4, so 1 comma 4 is there. In this way, we observe that the criterion of transitivity is satisfied by each and every element of R. So in general, we may write it as A, B, C belongs to A. For all A, B, C belongs to A, B belongs to R, and B, C belongs to R, implies that A comma C belongs to R. So R is transitive relation. So we may conclude that R is reflexive and transitive but not symmetric. Thus, we may say that R is reflexive and transitive but not symmetric. Now let us talk about fourth part of first sum. Here R is given a set in Z, where Z is the set of integers. So relation in a set Z means relation R from Z to Z, where R is defined as the set of ordered pair x comma y, where x minus y is an integer. So here we have to check reflexivity of the relation. So let A is an integer, A belongs to Z. So 0 is an integer. So by this argument, every element A is related to itself under this relation. So A comma A belongs to R. So every element of Z is related to itself. So here R is a reflexive relation. Now let us talk about symmetry. Here we take two arbitrary elements A and B from Z, that is two arbitrary integers. If A comma B belongs to R, implies that A minus B is equal to an integer. So it implies that B minus A must also be an integer, because if A minus B is a positive integer, b minus a must be its additive inverse. That means having the same absolute value but opposite sign. So b minus a is also an integer. As for example, for clarification, I take 1 and 3, two integers. So 1 minus 3 is equal to minus 2, which is an integer. So 3 minus 1 will be 2, which is also an integer. So for every a and b, if a comma b belongs to R, a minus b must also belongs to R. B minus a belongs to R. So R is a symmetric relation. Now let us talk about transitivity of. If we take three arbitrary elements a, b, c from the set of integers and let a comma b belongs to R and b comma c belongs to R, it implies that a minus b is an integer and b comma c belongs to R implies that b minus c is also an integer. If we add them up, minus b is cancelled by plus b and we get a minus c on the left hand side, and on the right hand side we get the sum of these two integers, and obviously the sum of two integers is also an integer, so we may write it as an integer. So it implies that a comma c must also belong to R. So we have shown if a comma b belongs to R and b comma c belongs to R, then a comma c must also belong to R. So we may conclude that R is a transitive relation. So by above discussion, we have shown that R is reflexive as well as symmetric as well as transitive. So we may conclude at last R is reflexive, symmetric and transitive as well. So in short, we may say that R is an equivalence relation. Now we come to fifth part, which has 5 subparts. So we have taken A part. Here R is given as a relation in a set A of human beings in a town at a particular time, given by R is a set of ordered pair x comma y where x and y work at the same place. So let us check the reflexivity. So let us take an arbitrary element out of domain. X belongs to A. We may say that X is a person in the town A. So if we write this statement, X and X work at the same place, then this statement must be true because everyone works where he works. So X and X work at the same place. It is a true statement. So under this relation, every person is related to himself or herself. So we may say that X comma X belongs to R. So under this relation, every element of domain A is related to itself. So R is said to be a reflexive relation. Now let us talk about symmetry. For checking symmetry, let us take two arbitrary elements of domain A, X and Y. Or we may say that X and Y are two persons from the town A, such that X comma Y belongs to R. According to definition, if X comma Y belongs to R, then X and Y work at the same place. So as we observe, X and Y work at the same place may also be written as Y and X work at the same place. That is, if we interchange X and Y in the statement, the meaning of the statement doesn't change. So it implies that Y comma X must also belong to R. So we have shown that if x comma y belongs to R, then y comma x must also belong to R. So the criterion of symmetry is satisfied. Thus R is a symmetric relation. Now let us talk about transitivity. For transitivity, let us take three arbitrary elements x, y, z from domain A, or we may say that x, y, z are three persons from the town A. So if x comma y belongs to R and y comma z belongs to R, then according to definition, x and y work at the same place, and y comma z belongs to R, so y and z work at the same place. Obviously, when x and y work at the same place and y and z work at the same place, then ultimately x and z must also work at the same place. So we may say that x and z work at the same place. So it implies that x comma z belongs to R. So we have shown that if x comma y belongs to R and y comma z belongs to R, then x comma z must also belong to R. So criterion of transitivity of a relation is satisfied. Thus we may say that R is a transitive relation. So we have observed that R is reflexive as well as symmetric as well as transitive. So R is an equivalence relation in this case. Now the B part of fifth part of question number 1. R is defined as an ordered pair x comma y where x and y live in the same locality. As it is very similar to the first part, so I am leaving it here. I am not going to solve it. You better try it yourself, because as verbally I can explain it. X and y live in the same place. If we replace y here by x and we write x and x, statement will be x and x live in the same locality, which is a true statement. Then we may say that R is a reflexive relation. And if the statement x and y live in the same locality may be written as y and x live in the same locality, so we may say that if x comma y belongs to R, then y comma x must also belong to R. So in this way this is symmetric, and if we take three arbitrary element x, y, z such that x comma y belongs to R and y comma z belongs to R, then x and y live in the same locality and y and z live in the same locality. So it implies that x and z live in the same locality. So we may say that x comma z must also belong to R. So in this way this is transitive also. So I have given a verbal clarification because I have explained the first part, which is very similar to this one. Now the third part, C part of the fifth part, is given as R is a relation x comma y such that x is exactly 7 centimeter taller than y. Taller than y. So reflexivity. Since no person can be taller than himself or herself, so we cannot say that x is exactly 7 centimeter taller than x. It will be a false statement. So that means under this relation no element is related to itself. So in general statement we may write it as x belongs to A, x is not exactly 7 centimeter taller then x. X is not exactly 7 centimeter taller than x because no one can be taller than himself or herself. So x comma x does not belong to R. So here R is not reflexive. Now let us talk about symmetry. So for symmetry, let us take two arbitrary elements x and y. For all x and y belongs to A, if x comma y belongs to R, implies that according to definition x is exactly 7 centimeter taller than y. So obviously if x is exactly taller than y, then y may not be taller than x, y must be shorter than x. So it implies that y is not exactly 7 centimeter taller than x. So it implies that y comma x does not belong to R. So if x comma y belongs to R, then y comma x does not belong to R. So we may say that R is not symmetric also. R is not a relation. Now let us talk about transitivity. For all x, y, z belongs to A, if x comma y belongs to R and y comma z belongs to R, it implies that x is exactly 7 centimeter taller than y, and y is exactly 7 centimeter taller than z. Then it implies that x is exactly 14 centimeter taller than z. Since x is exactly 7 centimeter taller than y and y is exactly 7 centimeter taller than z, then obviously x is exactly 14 centimeter taller than z. So we may say that x is not exactly 7 centimeter taller than z. So it implies that x comma z does not belong to R. So we have observed in this case that R is neither reflexive nor symmetric nor transitive. Now we come to fifth D part, where R, again A to A, where A is the set of the persons of a town and R is defined as ordered pair x comma y, where x is wife of y. So for reflexivity, we may take any arbitrary element x from domain. So as obviously x is wife of x is a false statement because no one can be wife of herself or himself. So no element A is related to itself under this relation. So we may say that x is not wife of x. So it implies that x comma x does not belong to R. So R is not a reflexive relation. Now let us talk about symmetry. Now for symmetry, we take two arbitrary elements x comma y belongs to A such that x comma y belongs to R. Suppose x comma y belongs to R. Now we have to check whether y comma x will also be element of R or not. So x comma y belongs to R implies that x is wife of y. Then obviously if x is wife of y, then y is husband of x, not wife of x. So y is husband of x. So it implies that y is not wife of x. It implies that y comma x does not belong to R. So R is not symmetric. Now let us talk about transitivity. Now let us take x, y, z, three arbitrary elements of domain A, such that x comma y belongs to R. If x comma y belongs to R, then it implies that x is wife of y. It means x must be a female and y must be a male. So y comma z will be y is a wife of z, while y is a male. So a male cannot be a wife of a male. So that means it is not possible that the relation can have y comma z if it has x comma y. So here y comma z cannot be contained by R. That is, the situation in which we can check the transitivity is not possible in this relation. That means transitivity of the relation may not be checked. And as I have told you, if transitivity of a relation cannot be checked, it is considered to be a transitive relation. So here we may say that transitivity of the relation cannot be checked. Thus, R is a transitive relation. Now let us talk about question number 2, in which R is a relation, the set of real numbers. R in the light font indicates the relation, and the R in the dark font indicates set of real numbers. And R is defined as the set of ordered pairs A comma B, where A is less than or equal to B square. Now we have to prove it that R is neither reflexive nor symmetric nor transitive. So let's do it. First we have to discuss reflexivity. So now we may consider any number between 0 and 1, say 1 upon 2, 1 upon 3, 1 upon 4, any number we may take. So let us take 1 upon 2, which is obviously a real number. It belongs to the set of real numbers, but half is greater than half square. So it implies that 1 upon 2 is not less than or equal to 1 upon 2 square. It implies that 1 upon 2 comma 1 upon 2 does not belong to relation R. So R is not reflexive. Though we may give many other examples, 1 upon 3, 1 upon 4, 1 upon 5, but it is sufficient to give only one example of a number which is not related to itself, because it is necessary that each and every element of the domain is related to itself. So even if only one element is not related to itself, the relation may not be reflexive. Now we have to discuss symmetry. suppose two elements as 2 and 5, both are real numbers. So obviously 2 comma 5 belongs to R since 2 is less than 5 square. But if we interchange the order of these numbers, so 5 is not less than or equal to 2 square, because 2 square is 4 and 5 is neither less than 4 nor equal to 4. So it implies that 5 comma 2 does not belong to R. So we may say that R is not symmetric. Now we have to discuss transitivity of the relation. So let us choose three numbers as 1 upon 2, minus 1 and 1 upon 4, which are real numbers obviously. 1 upon 2, minus 1 and 1 upon 4, all the three are real numbers. So as we know, 1 upon 2 is less than minus 1 square, because minus 1 square is 1 and half is less than 1. So it implies that 1 upon 2 comma minus 1 belongs to R. Now if we consider minus 1 and 1 upon 4, so obviously minus 1 is less than 1 upon 4 square, because 1 upon 4 square is 1 upon 16, which is positive, and every positive number is greater than every negative number. So minus 1 is negative, it is less than 1 upon 16. So it implies that minus 1 comma 1 upon 4 belongs to R according to given criterion. But if we consider the first and third one, that is 1 upon 2 and 1 upon 4. So 1 upon 4 square is 1 upon 16, which is obviously less than 1 upon 2. So we may say that 1 upon 2 is greater than 1 upon 4 square. So it implies that 1 upon 2 is neither less than nor equal to 1 upon 4 square. So according to given criterion of the relation, it implies that 1 upon 2 comma 1 upon 4 does not belong to R. So as we have shown, 1 upon 2 comma minus 1 belongs to R, and minus 1 comma 1 upon 4 belongs to R, but 1 upon 2 comma 1 upon 4 does not belong to R, which is the violation of the condition of transitivity. So the relation is not transitive. Thus we may say that R is not transitive. From above discussion, we may conclude that thus R is neither reflexive nor symmetric nor transitive. Now sum number 3 is R is given a relation in the set 1, 2, 3, 4, 5, 6. That is, the domain and codomain is the set of first 6 natural numbers, and R is defined as the set of ordered pairs A comma B, where B is equal to A plus 1. And we need to check whether relation R is reflexive, symmetric or transitive. So first we would like to change this relation into roster form, because it is already given in set builder form. If domain and codomain are finite and not very huge, it is always advisable to convert a relation from set builder form into roster form. So B is equal to A plus 1. So we have to take A as 1 first element of domain, and we have to substitute in this relation to find the corresponding value of B. So 1 plus 1 is equal to 2. So it implies that 1 comma 2 belongs to R. If A is equal to 2, then B is equal to 2 plus 1, that is 3. It implies that 2 comma 3 belongs to R. In the same way, A is equal to 3. And if we write A is equal to 6, then B becomes 6 plus 1 is equal to 7, but 7 does not lie in codomain, so this ordered pair is not possible. 7 does not belong to the set 1, 2, 3, 4, 5, 6. Thus, only these 5 ordered pairs are contained by the relation, so a relation can be defined in the roster form as the set of ordered pairs 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Now it is very convenient to discuss reflexivity, symmetry, and transitivity of the relation. So let's do it. As we know, no element of domain is related to itself. That is, there is no 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 ordered pairs in the relation. So it is not reflexive. Since 1, 1, 2, 2, and so on to 6, 6 do not belong to R. So R is not reflexive. Now let us discuss symmetry. As it is quite clear that reverse of any ordered pair is not contained by the relation 1, 2 is there but not 2, 1, 2, 3 is there but not 3, 2, and so on up to 5, 6. The reverse of any ordered pair is not contained. So we write in journal for all A, B belongs to set 1, 2, 3, 4, 5, 6. A, B belongs to R. Then B, A does not belong to R. So this is the violation of symmetry. So we may say that R is not a symmetric relation. Now let us talk about transitivity. So first we observe whether the transitivity of the relation can be checked or not. For that we need at least 2 ordered pairs such that the second component of one ordered pair is identical to first component of the other ordered pair, which is obviously present here. So we may check the transitivity of the relation. So by the criterion of the transitivity, if 1, 2 is there and 2, 3 is there in the relation, there must be 1, 3. So 1, 3 is not contained by the relation, so the criterion of transitivity is violated. So we may say that 1, 2 and 2, 3 both belong to R, but 1, 3 does not belong to R. Though we may also give the reason 2, 3 is there and 3, 4 is there, there should be 2, 4 for transitivity, but it is still not here 2, 4 any ordered pair. So here we may say 3, 4 is there, 4, 5 is there but not 3, 5, and 4, 5 is there, 5, 6 is there but not 4, 6. So we may give many reasons, but it is sufficient to give only one reason. So we have given 1, 2 and 2, 3 belong to R, but 1, 3 does not belong to R. Thus R is not transitive relation. So we come to the conclusion that the given relation is neither reflexive nor symmetric nor transitive. Now let us talk about sum number 4, which is R is a relation in the set of real numbers, which is denoted by R in dark font here. So domain and codomain is the set of real numbers, and a relation is defined as the set of ordered pairs A comma B where A is less than or equal to B. We have to prove here R is reflexive and transitive but not symmetric. So let's do it. First, we need to discuss reflexivity. For all A belongs to set of real numbers, since we know well every real number is equal to itself, so it implies that A comma A must belong to relation R. So this way every real number is related to itself, which is the required criterion for reflexivity of a relation. So we may say that R is a reflexive relation. Now let us talk about symmetry. Here we assume two arbitrary elements A comma B, which belongs to set of real numbers such that A comma B belongs to R, and this is because A is less than B. Because according to criterion, if A is less than or equal to B, A comma B is contained by the relation. So if A is less than B, then obviously A comma B is contained by the relation, but it implies that B is greater than A. So we may say that B is neither less than or equal to A. If B is greater than A, that means it is neither equal to A nor it is less than A. So it implies that B comma A does not belong to R. So we have shown that if A comma B belongs to R, then B comma A does not belong to R. So this is the violation of the criterion of symmetry. So we may say that R is not symmetric. Now let us talk about transitivity. So let us take three arbitrary elements A, B, C from the set of real numbers such that A comma B belongs to R and B comma C belongs to R. It implies that A is less than or equal to B and B is less than or equal to C. So obviously if A is less than or equal to B and B is less than or equal to C, so A must be less than or equal to C. So it implies that A comma C belongs to R. So we have shown if A comma B belongs to R and B comma C belongs to R, then A comma C must also belong to R. So we may say that R is a transitive relation. So in this way we have proved that R is a reflexive relation and R is a transitive relation, but R is not a symmetric relation. Now here we come to sum 5, and in this R is a relation in the set of real numbers, and R is defined as the set of ordered pairs A comma B with the condition that A is less than or equal to B cube. That is, first element must be less than or equal to the cube of the second element. So we need to check whether R is reflexive, symmetric or transitive. So let us talk about reflexivity first. Let us take any negative number, say -2. So obviously -2 cube is equal to -8, which is obviously less than -2. So we may say that -2 is greater than -2 cube, and that's why minus 2 comma minus 2 does not belong to R. So we may say that R is not reflexive relation. Now let us talk about symmetry of the relation, because we have changed the page. So for the reference we have written the relation again. Now symmetry we have to discuss. So let us take two elements, say 2 and 9. Both are real numbers, and obviously 2 is less than 9 cube, so it implies that 2 comma 9 belongs to R. But 9 is greater than 2 cube, which is equal to 8. 9 is greater than 8. So it implies that 9 is neither less than nor equal to 2 cube. So it implies that 9 comma 2 does not belong to R. So we have shown if 2 comma 9 belongs to R, then 9 comma 2 does not belong to R, though 2 and 9 both are real numbers. So we may say that R is not symmetric. Now let us talk about transitivity of the relation. So let us take three real numbers as 64, 4 and 2. All the three are real numbers, and obviously 64 is equal to 4 cube. So as the criteria for the relation is given, if first element is equal to cube of the second element, then order pair exists, or first element is less than the cube of the second element, then also the order pair can exist. So 4 cube is equal to 64. So we may say that 64 is equal to 4 cube. It implies that 64 comma 4 belongs to R. Now if we talk about 4 and 2, so obviously 4 is less than 2 cube, because 2 cube is 8 and 4 is less than 8. So it implies that 4 comma 2 belongs to R. But if we take the first and the third element, that is 64 and 2, so obviously 2 cube is 8 and 64 is not less than 8, neither it is equal to 8. So 64 is greater than 2 cube. It implies that 64 is neither less than nor equal to 2 cube. So we may say that 64 comma 2 does not belong to R. So we have shown, though 64 comma 4 belongs to R and ordered pair 4 comma 2 belongs to R, but 64 comma 2 does not belong to R. Thus R is not transitive. So we may conclude that R is neither reflexive nor symmetric nor transitive. Question number 6. R is a relation in the set 1, 2, 3, that is domain and codomain, are the same set, the set of first three natural numbers 1, 2, 3, and R is defined as the set of ordered pairs 1, 2 and 2, 1, and we have to show that R is symmetric but neither reflexive nor transitive. So let us talk about symmetry first, because we have to show that R is symmetric. So obviously there are only two elements in the relation 1, 2 and other is 2, 1. So reverse of 1, 2 is 2, 1 and reverse of 2 comma 1 is 1 comma 2. So we may say that each and every element of a relation R has its reverse in it. So we may write it in for all A, B belongs to set 1, 2, 3. If A comma B belongs to R, then B comma A also belongs to R. So R is symmetric. Now we talk about reflexivity. So obviously for the reflexivity, each and every element of the domain should relate itself. So, but here 1 comma 1, 2 comma 2, 3 comma 3 are not contained by the relation. So these ordered pairs are not there in the relation. We may say that no element of domain is related to itself, since 1 comma 1, 2 comma 2, 3 comma 3 do not belong to R. So R is not reflexive. And if we talk about the symmetry, so obviously 1 comma 2 belongs to R and 2 comma 1 belongs to R. So the criterion of symmetry can be checked because the second component of the one ordered pair is identical to first component of the second ordered pair. So for the transitivity, the first element of first pair must relate the second element of second pair, that is 1 1 should be there for transitivity, but it is not contained by the relation. But 1 comma 1 does not belong to R, so the criterion for transitivity of a relation is violated. So we may say that R is not transitive. So in this way we have shown that R is symmetric but neither reflexive nor transitive. Now we come to sum number 7, where R is a relation in a set A, that is domain and codomain are A, and the set A is defined as set of all books in a library of a college, and a relation R is defined as the set of ordered pairs x comma y such that x and y have same number of pages. And we have to show that R is an equivalence relation. That is, we have to show that R is reflexive, symmetric as well as transitive. So let us talk about reflexivity first. For reflexivity, let us take an arbitrary element x from the set A. That means any book from the set of all the books in the library. We have taken x. So as we know that by the given criterion of the relation, x and y have the same number of pages, x and x have same number of pages. Obviously this statement is true, so it implies that x comma x belongs to R. So this way we have proved that each and every book of the set of all books in the library is related to itself under this relation. So R is a reflexive relation. Now let us talk about symmetry. For symmetry, let us take two arbitrary elements x comma y from set A such that x comma y belongs to R. It implies that x and y have same number of pages. Obviously this statement may also be written as y and x have same number of pages. So it implies that y comma x belongs to R. So we have shown that if x comma y belongs to R, then certainly y comma x must also belong to R. So in this way R is a symmetric relation. Now let us talk about transitivity. For transitivity, let us take three arbitrary elements x, y, z from set A such that x comma y belongs to R, and the second ordered pair y comma z belongs to R. According to definition of relation, x and y have same number of pages, and y comma z belongs to R, that is y and z have same number of pages. So obviously if x and y have same number of pages and y and z have same number of pages, so certainly x and z must also have same number of pages. So we may write it as x and z must have same number of pages. So it implies that x comma z must also belong to R. So we have shown when x comma y belongs to R and y comma z belongs to R, then rationally x comma z also belongs to R. So in this way the criterion of transitivity of the relation is satisfied. So we may say that R is a transitive relation. So we may conclude that since R is reflexive, symmetric, and transitive as well, therefore R is an equivalence relation. Now let us talk about sum number 8, in which R is a relation in a set A, that is A to A, where A is the set of natural numbers from 1 to 5, and R is defined as the set of ordered pairs A comma B, where modulus A minus B is even. And we have to prove that R is an equivalence relation. So let's prove it. So first we have to discuss reflexivity of the relation. So put a subheading reflexivity. Now let us take an arbitrary element A from set A. It could be 1, 2, 3, 4 or 5. So we have taken arbitrary element. This is any one of these 5 elements. So modulus A minus A is equal to modulus 0, and that is equal to 0. Obviously 0 is an even number, which is even, So by the definition, if modulus A minus B is an even number, then A comma B exist in the relation. So we have shown A minus A, that is for any element of set A, the difference of the number from itself is equal to 0, which is an even number. So every element is related to itself. A comma A belongs to R. So R is a reflexive relation. Now let us talk about symmetry. So here we may take any two arbitrary elements out of these 5 from A such that A comma B belongs to R. It implies that modulus A minus B is even. So if modulus A minus B is even, so modulus A minus B may be written as twice lambda, means any multiple of 2. So it implies that modulus minus B minus A modulus is equal to twice lambda. That is, we have taken minus out of these two terms within modulus sign, and it implies that modulus b minus a is equal to 2 lambda. That is, modulus b minus a is also an even number if modulus a minus b is an even number. So modulus b minus a is even. So by the definition, if modulus b minus a is even, then b comma a must also belong to R. So we have shown that for any two elements a and b out of these 5 elements of set A, if a comma b belongs to R, then b minus a also belongs to R. So this way R is symmetric relation. Transitivity. For transitivity, let us choose 3 arbitrary elements out of 5 elements of set A, B, C from A, such that by definition of relation, it implies that modulus A minus B is even, and also modulus B minus C is even. So it implies that modulus A minus B can be written as a multiple of 2, say 2 lambda, and in the same way modulus B minus C may also be written as multiple of 2, say 2 mu. So it implies that A minus B is equal to plus minus 2 lambda and B minus C is equal to plus minus 2 mu. If we add them to, if these two equations are added, then minus B will cancel plus B and we get A minus C. Here A is left and here minus C is left, minus C. B is cancelled by B and A minus C is left on the left hand side, and on right hand side we get plus minus 2 lambda plus minus 2 mu, out of which we may take plus minus 2 common within a bracket lambda plus mu. So obviously plus minus 2 is common out of this bracket, so it must be a multiple of 2. So we may say that A minus C is also equal to an even number. So it implies that modulus A minus C is even, and so A comma C belongs to R. So argumentally we have shown that if for any 3 elements A, B, C out of the given elements of A 1, 2, 3, 4, 5, if A comma B belongs to R and B comma C belongs to R, then A comma C must also belong to R. So in this way this relation is transitive as well. So we may conclude that R is reflexive, symmetric, and transitive as well. Thus, R is an equivalence relation. Now, in the second part, we have to show that all the elements of the set 1, 3, 5 are related to each other under this relation. So let us take 1 and 1, modulus 1 minus 1, which is modulus 0, that is 0, which is even, So 1 comma 1 belongs to R. Similarly, we may show that 3 comma 3 and 5 comma 5 must also belong to R, because as we have shown for 1 comma 1, modulus 1 minus 1 is equal to 0, which is an even number. Similarly, we may show that 3 minus 3 modulus is also equal to 0, and 5 minus 5 modulus is also equal to 0. Now we have to take 1 and 3. So modulus 1 minus 3, that is equal to modulus minus 2, that is 2, and modulus 3 minus 1, that is also equal to 2. In both ways, this is even number. Whether we subtract 1 from 3 or 3 from 1, the modulus is equal to 2, which is an even number. So it implies that 1 comma 3 and 3 comma 1 both belong to R. Now let us take 3 and 5 in the same way. Modulus 3 minus 5 is equal to modulus 5 minus 3 is equal to 2, which is an even number. So it implies that 3 comma 5 and ordered pair 5 comma 3 also belong to R. Now let us take 1 and 5. So modulus 1 minus 5 is equal to modulus 5 minus 1 is equal to 4, which is an even number. So it implies that 1 comma 5 and 5 comma 1 both belong to R. So in this way we have shown that all the elements of the set 1, 3, 5 are related to each other under this relation. Now as a third part, further we have to show that all the elements of the set 2 comma 4 are related to each other. So let us take 2 and 2. So modulus 2 minus 2 is equal to modulus 0, that is 0, which is even. So 2 comma 2 belongs to R. Similarly, we may show that 4 comma 4 belongs to R. Now further, if we take 2 and 4 together, so modulus 2 minus 4 is equal to modulus 4 minus 2 is equal to 2, which is even. So under this given relation, ordered pair 2 comma 4 and 4 comma 2 both belong to R. So we have shown that all the elements of the set 2 comma 4 are related to each other. Now further, in the fourth and the last part of the sum, we have to show that no element of the set 1, 3, 5 is related to any element of the set 2 comma 4. So let us take 1 and 2 out of them. Modulus 1 minus 2 is equal to modulus 2 minus 1 is equal to 1, which is odd, or we may say which is not even. So 1 comma 2 and 2 comma 1 do not belong to R. Now let us take 1 and 4 in the same way. We may show that modulus 1 minus 4 is equal to modulus 4 minus 1 is equal to 3, which is odd. So 1 comma 4 and 4 comma 1 do not belong to R. If we take 3 and 2 in the same way, if we take 3 and 2, modulus 3 minus 2 or modulus 2 minus 3 is equal to 1, which is again odd. So 3 comma 2 or 2 comma 3 do not belong to R. And if we take 3 and 4, so modulus 3 minus 4 and modulus 4 minus 3 both are equal to 1. which is odd. So 3 comma 4 and 4 comma 3 are not the elements of the relation R. Now if we take 5 and 2, so modulus 5 minus 2 or modulus 2 minus 5 is equal to 3, which is again odd. And if we take 4 and 5, so modulus 5 minus 4 and modulus 4 minus 5 is equal to 1, which is again odd. So 5 and 4 do not relate with each other. So I leave the solution here. Further you may proceed it, as I have given verbal clarification for that. So here if we come to 9th sum of exercise 1.1 of NCERT, it is given, show that each of the relation R in the set A, where set A is defined as a set of x belongs to Z and x is greater than or equal to 0 but less than 12, given by the relations are given as, first part, R is a set of ordered pair A comma B where a modulus A minus B is a multiple of 4, and second part is R is equal to the set of ordered pair A comma B where A is equal to B. So I think this sum is very similar to 8th one, which I have explained already. So I am leaving 9th one. You should try yourself. Now in sum 11, R is a relation in the set A, that is domain and codomain both are A, and the set A is given as a set of points in a plane, and R is defined as a set of ordered pair P comma Q where distance of the point P from origin is the same as the distance of Q from the origin. So we may also write the relation R in simpler way. R is a set of ordered pair PQ such that OP is equal to OQ, because O is generally used to denote origin. So distance of P from origin, that may be written as OP, and distance of Q from origin, that may be written as OQ. So it is better to write the relation in this way. So now reflexivity let us take an arbitrary point from set A, say P belongs to A, since OP is equal to OP. This is quite easy to understand. OP is equal to OP. It implies that P comma P belongs to R. So in this way, every point contained by the set A is related to itself, so R is reflexive. Now let us talk about symmetry. For symmetry, let us take two arbitrary points P and Q from the set A such that P comma Q belongs to R. It implies that OP is equal to OQ. The distance of P from origin is equal to distance of Q from the origin, as given by the definition of relation in the sum. So obviously this statement may also be written as OQ is equal to OP. If OP is equal to OQ, then OQ is equal to OP. There is no difference. So it implies that with this condition we may write Q comma P belongs to R. So we have shown if P comma Q belongs to R, then Q comma P also belongs to R. So in this way R is symmetric. Now let us talk about transitivity. For transitivity, let us take three arbitrary point PQ S from the set A such that P comma Q belongs to R and Q comma S belongs to R. It implies that by the definition OP is equal to OQ and OQ is equal to OS. Observing these two statements, we come to the conclusion which is quite clear. When OP is equal to OQ and OQ is equal to OS, then OP must be equal to OS. So it implies that P comma S belongs to R. So we have shown if P comma Q belongs to R and Q comma S belongs to R, then P comma S also belongs to R. So in this way, R is transitive as well. And since R is reflexive, symmetric and transitive, it is an equivalence relation. Hence, R is an equivalence relation. Further, in the same sum, we have to show that the set of all the points related to P, which is not origin, is a circle passing through P with origin as center. So let us take P1, P2, P3 and so on from set A such that is P1 comma P, P2 comma P, P3 comma P and so on, all belong to R. It implies that OP1 is equal to OP, OP2 is equal to OP, OP3 is equal to OP and so on, which is only possible when P and P1, P2, P3 and all these points lie on a circle with origin as center. Like this, OP1 is equal to OP, OP2 is equal to OP, OP3 is equal to OP and so on. This is only possible with this condition: OP or OP1, OP3, OP4, OP5, OP6 and so on, all are equal to radius of the circle with center O, that is origin. Now we come to the next problem, that is 12th one, where R is a set in set A, where set A is given as a set of all triangles and R is the relation which is defined as the set of all ordered pairs T1 comma T2, where T1 is a similar triangle to T2. Then we have to show that R is an equivalence relation. So let us start with reflexivity. Let us take any arbitrary element, say T1, from the set A, any triangle. So as we know that every triangle is similar to itself, so we may write it as T1 is similar to T1. Then by the definition, if T1 is similar to T2, then T1 comma T2 belongs to R. So if T1 is similar to T1, it implies that T1 comma T1 belongs to R. So in this way, every element of A is related to itself. That's why R is reflexive. Now let us talk about symmetry. For symmetry, let us take two arbitrary elements T1 and T2 from the set A. So these are two triangles T1 and T2 from set of all triangles, that is set A, such that T1 comma T2 belongs to R. According to definition of relation, T1 is similar to T2, as it is quite clear that this statement may also be written as T2 is similar to T1. So it implies that T2 comma T1 belongs to R. So we have shown if T1 comma T2 belongs to R, then T2 comma T1 must also belong to R. So in this way, R is a symmetric relation. R is symmetric. Now let us talk about transitivity. For transitivity, let us take three arbitrary elements of set A, T1, T2 T3 belong to A such that T1 comma T2 belongs to R and T2 comma T3 also belongs to R. It implies that T1 is similar to T2 and T2 is similar to T3. And obviously, if T1 is similar to T2 and T2 is similar to T3, then logically T1 must be similar to T3. It implies that T1 comma T3 also belongs to R. So R is transitive too. So here we have shown that R is reflexive, R is symmetric, as well as R is transitive. So we may say that R is an equivalence relation. So in the same question, it is given that T1 is a triangle with the side 3, 4, 5, T2 is a triangle with side 5, 12, 13, and T3 is another triangle with sides 6, 8, 10. And the question is, which of the triangles among T1, T2 and T3 are related? So if we talk about T1 and T2, and let us check the similarity of these two triangles. T1 has the side 3, 4, 5 and T2 has the side 5, 12, 13. So as we know that if two triangles are similar to each other, their sides must be proportional. So if we take the ratio of first two sides, so we get 3 upon 5, and if we take the ratio of the second two sides, 4 upon 12, which is equal to 1 upon 3. So it's quite clear that these two ratios are not equal. 3 upon 5 is not equal to 1 upon 3. So since the sides of the triangle T1 and T2 are not proportional, we may say that T1 comma T2 does not belong to R. If we consider T2 and T3, so T2 has side 5, 12, 13 and T3 has the sides 6, 8, 10. Now if we check the ratios of the sides, we get 5 upon 6 the ratio of the first two sides, and the ratio of the second two sides is 12 upon 8, which is quite different from 5 upon 6. So 5 upon 6 is not equal to 12 upon 8. So here again the sides are not proportional, so it implies that T2 comma T3 are not related. Now let us talk about T1 and T3. So T1 has the side 3, 4, 5. T3 has the sides 6, 8, 10. Now if we take the ratio of the first two sides, we get 3 upon 6, which is equal to 1 upon 2. If we take the ratio of the second two sides, that is 4 upon 8, which is again equal to 1 upon 2. And if we take the ratio of the third sides, we have 5 upon 10, which is equal to 1 upon 2 again. So as we have seen that the sides of the triangles T1 and T2 are proportional. 3 upon 6 is equal to 4 upon 8 is equal to 5 upon 10, which is only possible when the triangles are similar to each other. So we may say that T1 is similar to T3, and that's why T1 and T3 are related to each other. So T1 comma T3 belongs to R. Now this sum 13 is given as show that the relation R defined in the set A of all polygons as R is the set of ordered pair P1, P2 such that P1 and P2 have the same number of sides is an equivalence relation. So what is the set of all the elements in A related to the right triangle T with the side 3, 4, 5? So this sum is quite similar to 12.1, the previous one, which I have already explained. So I think you should try it yourself. Yes, as far as the second part of the sum is concerned, as the criteria for two elements P1 and P2 to be related under this relation is P1 and P2 must have same number of sides. And here the set of all elements in the second part of the question, what is the set of all elements of A related to right triangle T with the side 3, 4, 5. Since the number of sides are concerned under the criterion of the relation, not the length of the sides. So here 3, 4, 5, the length of the three sides of a triangle has nothing to do with the relation. So it is only to make you confused. So don't get confused. That means every triangle has three sides. So set of all elements A related to triangle must be the whole set of triangles, because each and every triangle has three sides. Hope you have understood well. If you have not, please write in my comment section. I will clarify it again. Now the sum 14, in which R is the relation in set L, where L is the set of all lines in xy plane and R is the relation given as the set of ordered pairs L1, L2, where L1 is parallel to L2. And we have to prove that R is an equivalence relation. And obviously this is quite similar to the 12th one, which I have already explained, but I can't dare to skip two sums. So let us talk about reflexivity. Let us take any arbitrary element L1 out of the set L, any straight line L, and as you know that every straight line is parallel to itself, so we may say that L1 is parallel to L1, so it implies that L1, L1 belongs to R. So we have shown that each and every straight line from the set L is related to itself. So in this way R is reflexive. Now let us talk about symmetry. Now let us take two arbitrary elements L1 and L2 from the set L such that L1, L2 belongs to R. It implies that L1 is parallel to L2, and obviously if L1 is parallel to L2, it may also be written as L2 is parallel to L1. So it implies that L2, L1 belongs to R. So in this way we have shown for any arbitrary straight lines L1 and L2, if L1, L2 belongs to R, then L2, L1 must also belong to R. So in this way R is symmetric. Now let us talk about transitivity. For transitivity, let us take three arbitrary straight lines L1, L2, L3 out of all the straight lines in the set L such that L1, L2 belongs to R and L2, L3 belongs to R. It implies that L1 is parallel to L2 and L2 is parallel to L3. And obviously when L1 is parallel to L2 and L2 is parallel to L3, then L1 must be parallel to L3. It implies that L1, L3 must also belong to R. So in this way R is transitive too. So since we have shown that R is reflexive as well as symmetric as well as transitive, so R is an equivalence relation. Now as the second part of the same sum, we need to find the set of all the lines related to the line y is equal to 2x plus 4 under this relation. So that means every straight line which is parallel to this straight line will be related to it and as we know that in the form of straight line y is equal to mx plus c, here m is the slope of the straight line and c is the y-intercept. So since every parallel lines have same slopes, so any straight line which is parallel to this straight line must have the same slope, otherwise it may not be parallel to this straight line. So that means if m is the slope, that is in place of m there is 2, so 2 is the slope of this straight line, so every straight line whose slope is 2 will be related to this straight line. So there will be no difference in this term, that must be 2x. Yes, it can have any intercept on y-axis, so this term will be different and it can be any real number. So we may replace 4 by any arbitrary term, say y is equal to 2x plus c. C may be any real number. The set of straight line is given by this equation y is equal to 2x plus c. Now since the last two sum 15 and 16 are MCQs which are quite easy, so I'm not going to clarify this. If you have any problem related to these two sums, you may write in the comment section. I will try my best to answer. I hope you might have understood every sum. So please share, like and subscribe my channel. Thanks for watching.